Welcome to This Explainer. I am absolutely thrilled to guide you through today's topic. We're diving into a really fascinating concept in systems engineering known as the N9 problem. If you've ever heard engineers, IT professionals, or facilities managers bragging about how many nines of uptime their system has, you know it sounds incredibly impressive. But today, we're going to look under the hood and see what that actually means in the real world.
But before we start crunching the numbers, it's really vital to establish the boundaries of our study today. Just to be completely clear, this explainer is an independent, academic, educational work using my own lectures and original analysis. We're going to be using a purely generic cooling loop case study for our framework. So this is intended strictly for individual learners, students, educators, and university-affiliated researchers. We are not analyzing a specific facility here, and absolutely nothing in this presentation constitutes commercial, industrial, engineering, or investment advice. We're just creating a controlled environment so we can learn the fundamental principles of systems engineering together.
All right, let's dive right into our syllabus. We're going to start with the question, move on to the mathematics, and then tackle the independence problem. From there, we'll look at real design engineering, evaluate the economic trade-off, and finish up by defining the terms.
Section 1. The question. What do people actually mean when they confidently claim they have 5 nines? Well, the term nines simply refers to how close a system's availability is to 100%. So, if someone claims they have 5 nines, they're essentially claiming an availability of 99.999%. Over the course of a standard year, 5 nines translates to an annual outage budget of exactly 5.26 minutes. Sounds incredibly precise, doesn't it? But here's the catch. An exact number, like 5.26 minutes, is totally meaningless and honestly even dangerous to rely on unless you fully understand the system boundaries, the dependencies, and the assumptions that actually went into that calculation.
Moving right along to Section 2, the mathematics, calculating the nines.
Let's take a look at our baseline formula block on the screen. For our formula, n equals the negative base 10 logarithm of 1 minus a. Let a represent our availability fraction, which is just a number between 0 and 1. For our substituted numbers in units, if you're working with a percentage like p, it looks like this. N equals the negative base 10 logarithm of 1 minus p divided by 100. The result is your calculated nines. So, for our one-sentence engineering meaning, the number of nines is the negative base 10 logarithm of the unavailable fraction. Now let's see how this builds into real downtime over a whole year. Just take a look at the pattern here. 3 nines gives you about 8.76 hours of downtime per year. Add a 9 to get 4 nines, and your downtime plummets to 52.6 minutes. 5 nines, just 5.26 minutes. And 6 nines is a mere 31.5 seconds per year. So mathematically speaking, every single additional 9 drops your annual downtime by exactly a factor of 10. It scales perfectly.
Okay, let's apply this to a specific academic example. Imagine a generic cooling pump serving a critical loop. Strictly for this academic exercise, we're going to assume this single pump has a 99.9% availability. Following our formula block, our formula is n equals negative log base 10 of 1 minus a sub p. Our substituted numbers in units give us n equals negative log base 10 of 1 minus 0.999. The result is exactly 3 nines, or 8.76 hours of annual downtime. So the one-sentence engineering meaning is straightforward. A single generic component with 99.9% availability provides exactly 3 nines of reliability.
Now, what's really interesting is what happens when we attempt to improve the system by adding a second, identical cooling pump right next to it in parallel. We'll assume either pump can handle the full load, they fail independently, and automatic transfer works flawlessly. For our formula, the availability of the system equals 1 minus the quantity of 1 minus a sub p squared. For our substituted numbers in units, that's 1 minus the square of 1 minus 0.999, which simplifies to 1 minus 0.000001. The result? 0.999999. That gives us 6 nines or 31.5 seconds of downtime per year. So our one-sentence engineering meaning is, assuming perfect independence, parallel redundancy mathematically squares the failure probability. We just catapulted from 3 nines to a brilliant 6 nines. Our downtime went from hours to literally seconds. But I really have to warn you, while this math is absolutely flawless, it is not yet a credible design conclusion.
And that brings us to Section 3, the independence problem, the mathematical rug pull.
You see, our beautiful 6 nines calculation rested on a massive assumption, perfect independence. But what if both of those pumps rely on a single shared control system? Let's say that control system is highly reliable, with an availability of 99.99%, or 4 nines.
Watch what happens to the math. Our formula is availability of the combined system equals the availability of the parallel system multiplied by the availability of the control. Substituting our numbers, we get 0.999999 multiplied by 0.9999. The result is 0.999899001, which is approximately 99.99000%, or about 4.09s. So, our one-sentence engineering meaning: a single shared dependency drastically reduces the mathematical availability of a perfectly redundant parallel system. Think about that. A single shared dependency practically wiped out the entire benefit of having that redundant pump.
Which leads perfectly into Section 4, Real Design Engineering, Beyond the Math. Real-world constraints shatter these mathematical illusions instantly. A real design engineer has to ask some really tough questions. Sure, you physically installed 2 pumps, but can one actually carry the full load all by itself? Can it start automatically if the primary one fails? Do they run on entirely independent power sources and sensors? Are they sharing the exact same valves, the same headers, or the same heat rejection path? Can you even take one offline for maintenance without completely losing your redundancy? And crucially, what on earth happens during a common cause failure, like a massive facility power outage or a sudden flood? Just having 2 physically installed components simply does not automatically equal a truly independent system.
Let's move to Section 5, the economic trade-off, the cost of nines.
We saw a few minutes ago that, mathematically speaking, adding 9s is a beautiful linear progression, right? It drops down time by a factor of 10 every single time. But in physical reality, the cost of buying an extra 9 does not scale linearly. It explodes exponentially. Going from 4 9s to 5 9s doesn't just mean running out and buying another pump. It might mean buying an entirely separate power path, duplicating your entire control network, stocking very specific spare parts, paying to train specialized maintenance personnel, and dramatically increasing the day-to-day operating complexity of the entire system.
Let's wrap up our framework in Section 6, defining the terms availability versus reliability versus maintainability.
People actually use these terms interchangeably all the time, but they are profoundly different concepts. Reliability is simply the likelihood that a system will perform its function without failing. Maintainability, on the other hand, is about what happens after it inevitably fails. How fast and how effectively can you restore it to full service? And availability, those 9s we've been obsessing over, well, that's the big picture. It's the combined uptime over the total time. So the absolute crucial takeaway here is that availability isn't everything on its own. It's basically the child of how reliable your system is combined with how maintainable it is.
Let's look at one final calculation block to really cement this concept: steady-state availability. The formula is A equals MTBF divided by the quantity of MTBF plus MTTR. For our substituted numbers in units, if we translate those acronyms, that is mean time between failures divided by the sum of mean time between failures and mean time to recovery. The result is your steady-state availability. And for our one-sentence engineering meaning, availability reflects the combined effect of how rarely a system fails and how quickly it can be restored. This equation elegantly proves our last point. True availability perfectly reflects how rarely a system breaks down and how incredibly quickly your team can recover it when it does.
As we bring this explainer to a close, I want to leave you with a rather provocative question to ponder for your own studies. The N9 problem is a massive, complex systems challenge. It's not just about punching logarithms into a calculator or lazily counting how many redundant components you bought. You really have to ask yourself, which dependencies truly must be independent to survive real-world conditions, and is that mathematical improvement actually worth the exponential real-world cost?
It has been an absolute pleasure guiding you through this academic case study today. If you take away just one single thing from everything we've covered, let it be this fundamental truth of systems engineering. Calculated 9s are not automatically bankable availability.